Welcome to the last session for the IMFSE seminar series. So this is the final one of the year. We've seen a large number of very nice presentations from very different backgrounds. At the end of today, I'll return to that very shortly. But for today, we still have two presentations scheduled. One is by Juan Blond on performance-based design by for the company Basler and Hofmann. And then afterwards, Melchior Schepers from FESG is going to give a presentation as well. So with that, thank you all again. And I would like to invite the first speaker, so Juan Blond, to share the screen, and we are very interested to see that presentation. Yeah, perfect. We're seeing the screen now. It's not in presenter mode for the moment.
No.
Now it is perfect.
Can you hear me? Can you see the screen? So
yes,
I should begin, I think.
You're more than welcome. Thank you.
Hello, everybody. My name is Juan Blond. I'm IMFSE alumni, now working for 8 years for the Swiss company Basler and Hofmann. The company is also partner from the IMFSE, and today I'm happy to present you one example of the work that we are doing. It's about the industry hall that you are seeing here in this photo. And now, well, I will try to give you just a view of the work that we do and which is our vision of the fire safety. So just to introduce the project. So the use of performance base is allowed in Switzerland. We have like two possibilities, like Article 11, that you have a prescriptive solution, but you still have some light deviations from the prescriptive solution. Or you may also have the Article 12, that will be a completed performance-based project. So my first hint for all the students that are today hearing me. So when we are studying, we think we will do everything new and we will do just only performance-based. Well, that's okay. So don't forget that. But within the norm, there is still some space to provide very valuable solutions for our clients. So don't forget that. And to illustrate the project today, I will just follow this diagram that maybe you all already know. Just to illustrate that it's also very useful what you are learning right now. So to introduce the object that we are dealing with today, so we have an industrial hall which is devoted to the fabrication of metal components. So it's they just fabricate cars. It's a very big one, so 160 meters long with a width of 22 meters and very high. They have a just on-time supply concept, so there is not too much storage room, only for day production. And the requirements, the point was that the solution that I will present to you right now, the point was that they didn't identify the requirement at the very beginning of the project when someone may have done something different. So let's say a prescriptive solution. And well, that's something that you may need to face in the future, where a book solution doesn't work, and someone, and I hope it will be you, will need to think. It's really not so difficult. Well, we have two one-floor twin halls, so they are almost the same. They are divided by a 30 minutes fire-resistant wall. Each fire compartment is equipped with a smoke extraction system. We have smoke detection, but we don't have any sprinkler. And the point is that the fire norm doesn't require any fire resistance for the structure, but we didn't fulfill the distance between an existing building and the new building, and that's why at the end it was required to provide a 60-minute fire resistance for the new halls. So we can begin with our diagram. We already have the scope. We need to check the fire resistance. We have a goal. We must fulfill this 60 minutes for the structure, and we have an objective. We need to provide a constructible solution, minimizing or optimizing, so not or, and optimizing the construction time and the measures. So here was the situation that they began to build, and at some point came this requirement, and it was not possible to clad everything with a fire protective materials. And well, it's also interesting to know that maybe at the very beginning it wasn't be possible because of due to the complexity of the structure. But well, so the first question will be, it's really worth it to provide an alternative solution, and that's something that you need to think about, because sometimes you think, well, I will find a solution, and well, you can find a solution, but not you shouldn't sell a miracle which may disappoint the client, because it's also that the performance-based solution can be also demanding, and the communication with the client. So sometimes they think, well, if they provide a performance-based solution, everything will be very easy and very cheap, and no, that's not. It will be a better solution because that's a solution for the object that you have, but the communication is basic, so you need to tell the client what are you going to do. Coming to the qualitative analysis, so what, where, and how may something in our building burn? So we are working with metal, so we don't have too much combustible materials. We know that the storage quantity from combustible materials is reduced because they just have this just-on-time process. So everything is controlled, located, organized. We have a very big hole, so it doesn't seem too difficult to check that the entire building won't reach any critical temperature. So yeah, let's see what happens, and let's see if we really need to protect the entire structure. We go further in our diagram. So now we have the performance criteria. We must check and we must achieve that the structure won't reach the critical temperature. We will define the fire scenarios according to the storage content. We know where they will store the combustible materials. And the point was just to provide a fire resistance till a height where the anchor points for the installations were already installed. That's something like 6 meters above the floor, because till this height it was possible to provide a coating, a cladding with fireboards or whatever. But above that, a crane was already installed, so it was not possible to protect the structure. Beginning with the fire scenario, so just from easy to more complex, the first fire scenario, let's say like that we can imagine, will be just to check if the structure fulfill the demanded fire requirement just using the ISO curve, the standard test curve. So if that will be the solution, I won't be here presenting today this project. But the first point, that's not a representative fire scenario, since it will assume a constant temperature for the entire room, and that's not the situation that we have. The next one will be okay. And next step will be to take some parametrical time temperatures from the Eurocode, for example, but we are more or less in the same situation. So first one will be constant or a uniform temperature for the entire room, for the entire building, which is not representative, and also very important because of the size of the room, of the building, it won't be applicable. So we have to define the fire scenarios and we simulate the entire building with FDS. So the objects that we took as reference to define the fire scenario were pallets, because that was the combustible material that they have there. And just taking values from the literature, we may define the fire scenario. So we use the client provides us storage concept, and we could define how they storage their materials and how many combustible material we have, and we came into a fire curve. You will see these steps is you will see now in a video when the next pile of pallets will ignite. I will show you this video right now. So we have the fire here. The first one burns, ignites, and the other one ignites after some time. It's also important that you see here that's the smoke layer. So if I stop it here, for example, you see that the smoke layer is only on the top, but for example, this side is not affected by the smoke. So that gives us something to think about. And these green points that you see here, I will come to that. These are the sensors that we install. And if I come to the very beginning, you see that we don't have the structure itself, but we have the sensors measuring the temperature in the entire building. What we measure the adiabatic surface temperature. That's a temperature which can be used as input for the further structural analysis. And it represents somehow the effect of the radiation and the effect of the smoke temperature. And that's a really important point, because near the fire is the radiation, the dominant effect, but away, so the far field from the fire, will be the smoke. And that will be the maximum theoretical temperature that the structure may achieve. That doesn't mean that that's the temperature of the structure, but the structure cannot reach any higher temperature. That was what I was telling you before. So this is the structure, and we just put our sensor measuring this temperature, this adiabatic temperature, and the radiation effect in all directions. Just considering the form or the construction, so which size of the structure could be affected by the fire. Well, again, to assess the structural analysis, so the behavior of the structure, we also decide to begin from an easy analysis to a much more complex analysis. So if the steel temperature doesn't reach the 500 degrees, the mechanical properties of the steel remain almost unchanged, and well, you can say there is no problem for that. The next point, so we will see later, we are above this 500 degrees, so that was not useful. The next one was, okay, according to the rate of use of the structure and the loads that they must support, you can define a critical temperature for your structure, and this one is calculated according, so that's calculated in test using the ISO curve. So that gives us also an important information. And the last possibility will be just to go in a finite elements model. In our case, just so you know, we use this part, the maximal critical temperature, that was defined by the structural engineer. And so he told us that, well, our structure could load or will remain without any problem till something like 660 degrees. So if we see in this graph, that will be the ISO curve. These are the temperatures, the green ones are the temperatures that we measure. And the blue point line is the temperatures that it's a critical temperature. So we see that till something like 6 meters, our structure will reach the critical temperature if we don't do anything. But above 6 meters, the temperatures are not so high. So the point is that till 6 meters, in our case, the radiation is the main factor affecting the structure. And above that, we have the smoke and will be the convection and the smoke layer temperature, which is the dominant factor. So with these results, we could define a solution just to protect our structure till this 6 meters, 6 point something. That was the maximum free height of the structure that we could protect with fireboards without any demanding work. And that's important. So that also to communicate that you don't need each time to do a very complex finite element solution and just to calculate everything. There are other possibilities which provide a quite easy solution, cost effective. And I wanted to show you here that this comparison between the adiabatic surface temperature and the smoke temperature. So if we will only consider the smoke temperature, we can see here we are around this 300 degrees. But when we consider the adiabatic temperature, some parts of the structure may reach the critical temperature. So just considering the smoke temperature as factor or as input for the structural analysis, it's not enough. So as I said, here we have the solution. So that was the protection of one column. As you see here, that's the point where the crane is fixed to the column. And if we haven't do the solution, they will need to just to build a secondary entire new structure to fix the crane. That will be the book solution, just to take the crane to build a secondary structure just to fix it and protect the entire building steel structure with these fireboards. That's only one part of the solution. The other part is to define a concept of use and a concept of storage. So because if you begin to put all this fire load, or if you increase the fire load, the solution won't be valid anymore. But we define these storage areas where near the protected columns where they can store it, the necessary materials. And if they use cells, they are close ones, so that we kind of impede the propagation of the fire. So now we are at the end of our diagram. So we could say that the performance goals were achieved. We check the construction details and we work them with the constructor to provide a valid solution. And the last point was to prepare the documentation. And well, that's something that you probably already know. So a proper documentation must allow any third-party review. So it's not that you say that's the solution and no one can take it. That's not the idea. So you need to provide all the data from your study and your solution that someone could repeat it. But that doesn't mean to publish or to give your know-how. That's something that belongs to you or to your company, and that would make the difference with other companies. So just don't forget that you need to provide enough information, but there is some part that remains for you. So just to illustrate it, from the around 2,000 meters of steel that we will have protected, at the end we only protect 150. So that means a reduction of 92%, and that's only considering the material, because so it's also that we only protect the easy to be protected parts, and the ones near the ceiling, which could be almost impossible to protect, we didn't. And at the end, we provide a constructible solution, so the fabrication process remains intact. The architecture didn't need any modification, and any additional structure was required. So important also, so the results are only valid for this object and this use. A simulation doesn't mean always a easy solution, but it's a specific solution. So may require some additional measures. It's not that you don't need to protect anything. You protect only what it's necessary to protect in this case, or you implement the necessary measures only where they are needed. And very important, the concept of use, and the client must also know, and I come back to the point of the word communication. The owner, your client, must always know what you are doing, because that has those implications for him. To summarize, we think the performance-based concept provides alternative cost-efficient solutions and constructible sometimes. All parties must be involved from the very beginning. Goals must be clear, and we think that the use of these methods will increase, and it's in your hands. So you are creating the knowledge to make very safe fire safety concept. So thank you for your attention. If you have any questions, I will be happy to answer.
Thank you very much. Excellent. We've indeed started the questions in the chat, so everybody is invited to post questions there, or just raise your hand. I can give you the word. We have one first question already by Ferhat Ersin. It's asking if additional study was necessary for the justification of the 500 degrees Celsius limit for the authority having jurisdiction. Maybe Ersin, if you are available to unmute, maybe you can clarify that a little bit more.
I think I understand. Or I try to answer. So for this 500 degrees is just like the first approach, and for each structure, according to the, I think in English is the grade of use. So how is the structure used? So which load can the structure load? You can define some higher critical temperatures. Justification to the authorities, that was just the structural engineer. He just provides this. He provides this temperature according to the structural design, and that was all. I hope I answered the question.
Okay, yes.
Yeah,
that's excellent. I don't see another question here yet, which gives me the opportunity to maybe jump in and ask one as well. Actually quite related maybe, but so could you tell a bit more about the governmental oversight? So was there a governmental oversight? Did somebody else check the calculations, or did you have to convince other people? How did that go?
Well, in Switzerland we have something called, so just the translation will be the fire police. So we have kind of a expert, so that's the authority having jurisdiction, who will take the design. But it's so we make like intern control in the company, and also an extern from this fire police. They just check that everything, that your hypothesis and so for example the fire scenarios that you decide, they are reasonable, but they don't, for example, they don't simulate by themselves and check if you did well or not. So But we need to convince the authority having jurisdiction, if that was the question. Sorry.
Okay, thank you. That's perfect. From the audience, do you have other questions? Somebody who wants to raise something now? Maybe one quick one then additionally for me, because you just got me very curious there. You mentioned at some point that you should provide enough documentation, but that some part, I would say, remains for you, if I capture you correctly. Can you give an example or something which comes to mind on that?
Well, that's I think it's always difficult to say where the line is. I think that the point is, of course, you need to provide all information for that a third part could redo your calculations. But well, there are some points that so I mean, it's also the way of thinking, or how do you define the fire scenarios, or how do you do your FDS, how do you do your FDS model and all this stuff. I think that there are some parts that they are still know-how that belongs to the company, and it's not necessary to publish this part, but really important. And well, that was my message. So you need to provide also all the data, all the details that the one who is checking your review could go through all of it and well assess if your solution is correct or reasonable or not.
Perfect. That's very clear and clarified a lot for me. There's one additional question here by Darko. Darko, if you're available to unmute and just ask it out loud, it would be convenient.
Yeah, sure. Basically, I'm just curious because you use the Adiabatic surface temperature, and I was just curious whether it's maybe too conservative because you were already using like the bigger fire load than initially given by the client. I think he used like 30-40% more or something like that, if I remember correctly. Yeah. So I'm just like, how conservative do you go? Like, when do you stop? And when do you say, okay, this is enough? Like, maybe we should, yeah.
Well, the same logic that I show for the defining of the fire scenario. So from easy to complex. So if it works with a conservative solution and it's okay for all the parties, you don't optimize it, let's say, anymore. I think that the adiabatic temperature is the correct parameter here. If I will need to, let's say, optimize the solution, I will probably check if the fire scenarios of the load, the amount of good or combustible material that we use for the fire scenario, if I didn't have too much fire safety factor there. But the adiabatic temperature, I think, is the correct parameter for this assessment.
Okay.
Excellent. I mean, very enlightening example. So thank you very much for that, Juan. I would thank you here, and I would like to wrap up the first part of today and move to the second presentation.
Yeah, of course.
So, thanks again. So the second presentation is by Melchior Schepers. Melchior, are you already there? And if so, can you? Perfect. If you can share your screen, you're in the same room as I am most of the time.
Yes.
Excellent. Well, welcome. We're looking forward to your presentation as well.
Okay, perfect. I'll see if I can get it on the screen here. Okay, perfect. So I hope it's visible to everyone and I'm clearly audible. My name is Melchior Schepers. I'm a project manager at Fire Engineering Solutions Ghent. And tonight I'm going to talk to you about digitalization and innovation in fire safety, the things we're working on within FESG, and some of the trends that we see in the industry and that we're working on ourselves as well. Perhaps first a bit of background. The presentation is a bit of a different onset than the last one. But as a bit of background, Fire Engineering Solutions Ghent, the company I work for, we're a consultancy firm specialized in fire safety engineering. Founded in 2009 as a spin-off of Ghent University, and we specialize in performance-based design, but also in sprinkler design, basically anything that has to do with fire safety. We handle about 400 cases a year. A lot of them are performance-based analysis. A couple of derogation files or more than a couple each year as well. And currently we employ 17 fire safety engineers, a lot of which who are alumni of the local masters in Ghent or the international masters of fire safety engineering. So internally, we're divided in a couple of departments, Department of Buildings, Department Industry and Infrastructure, which mainly comprises large infrastructure projects such as tunnels. But what we're going to talk about today is mainly the R&D department and the trends going on in terms of digitalization and innovation. What we're going to look at is how do we cope with digitalization within FESG. Our answer to that was in the form of a set of web tools that we've developed and are still developing. And then in terms of innovation, we're going to look at BIM and fire safety, and then a new risk assessment framework that we're working on as well, which we've called FEARS.
Hi, Melchior, can I interrupt for a second?
Yes, of course.
I think sometimes I miss you for about 1 second or so. So
okay.
My first thing would be maybe if you don't go too fast, then if something drops out, we'll still understand everything.
Perfect. Okay, I'll switch off my camera. Perhaps that helps the connection.
Perfect.
So in terms of digitalization, first, the web tools, as I said. Now, if we look at digitalization, if we look at a formal definition, we can say it's the use of digital technologies to change a business model and provide new revenue and value producing opportunities. So it's the process of moving towards a digital business. And I think now more than ever that's obvious to everyone. During these COVID times, almost everything is digital. Meetings are even digital, like right now during this webinar. And what we've seen really internally as well, that it's really a continuous and iterative process. So it's really this ship and iterate approach that you need to take, where you try something, see what works, and then see how you can improve upon that. So where does this need come from, or how did we identify this need? Well, like I said, we can't deny it anymore. We live in a digital world. Information is available to everybody. Faster and faster, turnaround times are shorter than ever. And we really saw a clear need to address the demands of our clients as fast as possible and as accurately as possible. When we're sitting in a client's office, they didn't want answers next week, but right there and now, as fast as possible. What do we need here exactly? How are we going to address this problem? So we really saw that was key in terms of calculations, analysis, but also in terms of reporting, how to optimize the workflows in terms of automatic reporting, but also in terms of monitoring of processes. So as I said, our answer to that was in the form of a set of web tools, which we started developing somewhere last year. Because when we looked at the more traditional design methods, on the one hand, we have, of course, the hand calculations, the standards, which prescribe certain methods, or the more advanced methods like CFD or evacuation software. But when we looked at how we use those, that it's either Excel sheets mainly, or really complex software such as FDS, for example, Simulex, Pathfinder, those kind of things. But really often, the common misdemeanor was that it's really easy to make mistakes, even in those Excel sheets. If there's a reference to a certain cell that's not correct, the Excel is saved over and over, and it's just very tedious to adjust and easy to make mistakes. So that's why we set out to develop a set of web tools to make life as easy as possible for our colleagues in the first place, but for fire safety engineers in a broader perspective as well. So the web tools we've been developing are still developing right now, some of them as well. Parts of them have to do with design processes. So for example, calculations for firefighting water retention, fire load calculations, what's the fire load here in this building? If you have a given set of things that they store, how can we easily do a fire load calculation? Design for chef systems, so smoke and heat control systems. But then also in terms of legislation, because for us, fire safety engineers, for example, here in Belgium, the legislation might be really clear. But often when we're working with foreign companies or who are working on the same project, it's often not that clear what specific clauses of the legislation mean or how it should be interpreted. So that's why we set out to develop a tool, an online tool, a web tool as well, to guide other people through the Belgian legislation based on a set of questions, yes, no questions mostly, and then giving the answers or the specific guidelines or legislation that relates to that. And then also the more advanced web tools, which we're working on, such as automatic generation and checking of FDS code. So based on a set of questions, are there sprinklers present? Which guidelines should we follow? For example, the Swedish performance-based codes, the New Zealand-based codes. We can enter what we would like to have as a design guide. And then automatically part of the FDS code will be generated in terms of heat release rate, fire sizes, material properties even, etc. And then when you have done some final tweaking to the FDS code, perhaps manually even, you can upload it again and we have some error checking on that FDS code as well. And then last but not least, what we call the FBIM, the Fire Brigade Intervention Model, where we use a set of probabilistic parameters to check if it will be possible for the firefighters to intervene. Now, I know that this is quite a lot, so to give a bit of an example of this digitalization, we'll look at a case study in the next one, and more specifically this one for chefs, so for smoke and heat calculations, just to explain a bit more what we mean by web tools. So the smoke and heat control design in Belgium that typically takes place is according to the standards. The Belgian standard, which is the first one which you see here, the NBN S21. Of course, you've got the British guidelines, the BR 368, and then the European standard, the 12101 number 5. Now, how we used to approach this previously was in some kind of an Excel where you enter certain values and then you hope that all the references are correct and that you haven't made a mistake anywhere. And then you come up with some kind of standard design according to one of these standards. This design you can then validate, of course, using CFD, but the CFD process is, of course, a lot more tedious, takes much more time. And it's not necessary even in every case if it's a relatively standard building. So we want to come up with a new tool to do the design according to one of the standards. The design according to CFD, of course, there's always a point in validating your first design using CFD. For example, over here, this is an example of a CFD simulation of a smoke and heat control system, which is mechanically ventilated. And here, the higher extraction rate was effectively much worse than the lower effect and then the lower extraction rate, because there was much more entrainment of the surrounding air due to the higher air speeds of the inflowing air. So definitely, a simple design doesn't always work. But in a lot of cases, it at least can give you a starting point as to what would be a good solution for a smoke and heat control system. So we developed a graphic interface online, which anyone can log into, at least within the company right now, which make it a lot easier to do the design. So basically, as a little movie here is going to show, it's much less error prone. You select for which type of building you want to do the design. You select what occupancy it is. This is prescribed specifically in the Belgian norm, the NBN S21. You select if there's storage, what storage height there is, to enter some building parameters, such as the area of the smoke zone. And then automatically the design fire is prescribed according to the norm. And then immediately we have a graphic representation of what the standard predicts. So we can play around with those parameters and check how changing certain parameters affects the design that we've made for the smoke and heat control system. So that's really briefly this very first step of web tools and how we've coped with digitalization within FESG in terms of enabling a better design for our colleagues or employees. What else is going on in terms of digitalization and innovation is a recent focus that we've seen more and more on BIM and fire safety. Of course, BIM, it's a bit of a buzzword at the moment, where it's used more and more often in the building industry. So building information modeling, it's marked as one of the technological series in the fourth industrial revolution even. And it's really a handy tool where all of the architects, the designers, the AEC companies can really cooperate in one building model. But we saw that that fire safety was often left out a bit, and that the fire safety engineer didn't enter the design process until really the end of the project. And that's something that we wanted to improve upon. And that's why one of my colleagues, Sohaila Bigdali, is currently performing her PhD at Ghent University, which has as a research topic the usage of BIM within fire safety. And we're going to take a sneak peek here at what she's doing as well. So, as I said, BIM, more and more important these days. It's used in almost all of the bigger infrastructure projects, I think, these days. And it's really handy, of course, because we have this nice 3D model for complex building designs. We can evaluate CFD designs and even evacuation routes. So it's really a handy tool. But we often found, as I said, that we couldn't really use it until the end, or that architecture firms didn't contact the fire safety engineers until the very end of the design process, where not much could be changed anymore. So one of the questions that we asked ourselves was, how can the fire safety industry keep pace with this global rapid shift towards BIM? And then we identified a couple of different aspects in where we could have an impact by using BIM. So first of all, of course, the fire suppression system design, if we can route all the pipes, the pumps, and those kind of things from the beginning, that can lead to an optimal building design. Fire detection and alarm system design, the same story, and then even performance-based design studies, where the CFD model is automatically generated based on the BIM model, where there's information about the fire load that's used in the BIM model that can then be used for representative design fire. And then last but not least, compliance to building codes. So this was the first focal point for my colleague Sohaila, which she's been working on, compliance to building codes, and more specifically, automatically checking based on the BIM model if the building is going to be compliant to the legislative framework that is in place in a certain country. We saw that this process of checking the building plans of certain building was usually done by hand by fire safety engineers. It's a pretty tedious check, measuring widths of doors, measuring distances to evacuation routes. So it's not the most fun process. Certainly not if it changes a lot during revisions of architects, where there are little alterations to the building plans. So it's a really repetitive and tedious task. So one of the solutions we thought that might work was to develop an automated code compliance checker, where in the BIM model the check automatically happens based on a plugin. And there was a first prototype that was developed by my colleague, and which I'm going to show you here how it works. So it's a plugin that it's developed in Revit. You need to enter some information that might or might not be already in the BIM model. You can select the certain levels that are there. You might also need to indicate the fire load of a certain room. So what's the fire load that is in a certain room? Voila. And then you can see that a bunch of checks will happen in the following. So, well, what the plugin currently enables is checking of door widths, checking of evacuation distances. Of course, the goal is to incorporate in the future as much as possible. For example, to be able to check compartment sizes, to check if the correct fire rating is used of doors. Those are all kind of things that we're working on and that we hope to include in the plugin later on as well. For now, as I said, it's able to check door widths, evacuation distances, and those kind of things, just to make our life a bit easier. And also, of course, the life of the architects. If they can run this check automatically themselves, it's much easier for them to identify which things might have to change or where they'll have to make alterations to the model. So you can see that the elements of the building that do not conform to the legislation are highlighted. Over here we've got the path of travel and the distances between the furthest points in the rooms that are automatically highlighted and calculated as well. So that was one of the big focus points of us as well, BIM, life safety and code compliance. And then the last innovation that I'm going to present to you tonight is in terms of risk assessment frameworks, risk assessment framework, the development of a new risk assessment framework rather, which we've called FEARS, which is specifically for tunnels, life safety, and also building safety in tunnels. So FEAR stands for the Fire Integrated Environment for Risk Comprehension and Evaluation. It's a research project which is in cooperation with Ghent University and which is also partially funded through the Flemish government. And basically the incentive behind it was that there is currently no broad Belgian quantitative risk assessment or probabilistic risk assessment framework for fire safety in tunnels. And that we really wanted to come up with a holistic framework which takes into account much more than what is available today. Basically, the risk assessment framework that we're working on right now consists of a couple of layers. Layer 1, where we have a ventilation model and also an evacuation model, which was developed in-house. Also, it takes into account probabilistic boundary conditions. So, for example, distributions on the heat release rate, distributions on wind effects on the building or the tunnel, all those kind of things. And then in the second layer, we have the effects which are on a bit of a higher level, such as just firefighter intervention measures. A comparison, for example, between suppression or passive protection inside the tunnel, and also fire development. Will there be fire spread to other vehicles? And then in the last layer, we have traffic effects, the integration of the control that might be present for the ventilation system. And last but not least, also the consideration of cost. So costs in terms of business continuity, damage to the structure, but also reliability and maintenance in terms of of the installations inside the tunnel. As I said, the first layer, the most important one, with in-house models for ventilation and evacuation present. The second layer, which includes a couple of higher level effects, the fire brigade intervention model, once again, which takes into account the firefighters' intervention and the possible effect on fire spread towards other vehicles. And then we've got the third layer, taking into account the upper level effects such as traffic density, the control of the ventilation system, and then the different aspects of costs in terms of investment in a certain measure, for example, sprinklers or boosters on the tunnel ceiling. Maintenance, business continuity, and reliability, and the level of damage that were to occur if a fire would occur in the tunnel. The idea here is really to present an integrated design framework where all of these work packages influence one another and have an impact on one another as well. For example, the suppression, the cooling, the heat release rate reduction, that will have an effect on ventilation. The fire spread obviously is related to the time for firefighter attack. So all of these work packages are related, and we try to treat them in a holistic design. So perhaps as a summary for this last innovation, the goal is really to evaluate the effects of fire safety measures on different aspects: life safety, structural safety, the level of damage, business continuity. But also in terms of costs, investment, maintenance, repair cost. And so it's a really holistic, integral framework focusing on decision makers. So I want to set out clear performance metrics for authorities and provide them with a tool to objectively quantify design decisions. And I see that I've almost passed the 20 minutes, or even have passed the 20 minutes already. So that's what I'll keep it at for now, but I'll gladly answer any questions that there are.
Excellent, thanks a lot. So with this, the floor is open for any questions. For the moment, they're not arriving yet, but to everybody, you're also invited indeed to raise your hand. Just checking who's there. Dieter van Kerkhoven, so please, if you can unmute and ask a question, it's perfect.
Hello, good evening. Thanks for your talk. I was just wondering if, so the FERS software, is it meant for decision-making authorities or is it for designers?
Well, it's a bit of both. So it's a quantitative risk assessment framework, which obviously is aimed at fire safety engineer or designers of tunnels to evaluate the effects of certain measures. For example, a suppression system versus jet fan or a more standard ventilation system. But the goal of the framework eventually is to have an outcome in terms of life safety, of course, but also in terms of cost. So to objectify the different design decisions so that it would be easier for decision makers to quantify or to compare different design options. So it's a bit of both. Of course, it's the fire safety engineer that will use it and enter all the information, but the outcome should then enable the decision makers to make an objective choice.
Excellent. In the meantime, we also have a question by Marta Pasalenko. Is it possible to try any of these plugins?
Currently, some of the web tools are indeed available. Mostly of them are prototypes, which we currently use in-house to fine-tune them as well. Of course, we're not a non-profit organization, so the goal is eventually to make them available to the public or to other companies, perhaps even in the form of a license. We're still looking into that. The plugin will eventually probably become available as well. And FERS will also be a commercial framework in the end of as well. The web tools are in the most advanced stage right now, so those will be probably the available, the earliest ones.
Okay, we have a range of questions coming in here. Maybe first going a bit more into the QRA side, because we have some questions there. A question by Gunde Jomas. Gunde, if you can unmute to ask your question, it's perfect.
Sorry,
and otherwise I'll
do people asking it for me, but
yes.
it's in the traffic or the tunnel QRA, how is traffic conditions, load and vehicle type distribution, if it's truly, normally for an assessment on roads, one of the key things is how probable is an accident, because some designs are excluded if they're not very probable.
Yeah, no, definitely. It's a good point. The way that it's treated right now, or will be treated when it's fully incorporated, is by having just distributions for the heat release rate. So cumulative for distributions, which represent the probability of a certain heat release rate. For example, we could say that it's likely that, I don't know, 80% of the fires will be smaller than, let's say, 100 megawatts, or perhaps even 85 megawatts. And that the higher the heat release rate, the less likely the probability. So that relates in part to the distribution of vehicles. Of course, what we want to look at as well in the future is how is the distribution of vehicles going to change. For example, now we might have all conventional energy carriers such as petrol or diesel engines. How is that going to change in the future? That's something that we're looking into to definitely incorporate that as well. If we go, for example, more to new energy carriers in terms of electric vehicles, how will we have to take that into account? Will it be a different heat release rate, or will it just be in terms of toxic products that we need to change the concentrations? That's something that we're still looking into, but it's definitely a good point that we need to investigate it further a bit as well.
We have a related question also from Juan Blond, who asks, is the FEARS program applicable to other legislations?
Yeah, so it's not really bound to any legislation at the moment, since we don't have a framework in Belgium. It's not specifically bound to the Belgian legislation, so the goal is really to have a more general framework which is applicable anywhere if it's accepted by the authority having jurisdiction. So it's not that it's tied to a specific region per se.
Perfect. And we have two questions regarding the basically the making of those programs, really. One by Arjan Dexters and one by Stephen Welsh. Arjan asks what kind of background you're looking for at the FESG when hiring people. And maybe let's go there first.
It depends a bit. So
maybe I can just specify a bit. It's like, because making these tools probably requires knowledge in many different areas, which go far beyond what you learn in fire safety engineering. So we're just curious to know which type of backgrounds you need.
Yeah, so the head of the R&D department, Matteo Pacera, he has a background in terms of tunnel ventilation because he has a PhD in that. Most of us within FESG, or at least a couple of us, were quite fluent with a couple of programming languages in terms of mostly Python, that is. So I'm not going to say that is something that you learn per se during your education, but for example at university. Yeah, at least it would be good to have some programming skills, and then of course the knowledge of fire safety is a nicely added bonus here. It's important if you want to work on something like this to have at least to grasp a bit of how programming works and how to make sure that everything works as expected.
Thanks. And we have one question by Stephen Welsh as well, which is related to the QA procedure. So how do you actually check if your software is working correctly?
Yeah, no, for so most of the work packages which I've showed you, so the different work packages are first, the goal is to validate or verify them as individual work package in terms of, for example, the ventilation model that was developed, for example, compared to IDA tunnel or perhaps even CFD simulations. Same for the evacuation work package. So first validate them individually. And then later on, the goal is to verify the framework in comparison to other frameworks to see if the results at least hold up to some extent. For example, the methods in use in the Netherlands, the QRA methods. So that's the way we look at it right now. And of course, yeah, the University of Ghent, Ruben also plays a role in validating certain specific work packages.
Thanks a lot for that. Also, by the way, the connection issue appears to have been more on my side, so apologies.
Okay. Yeah.
So everything was very clear. I would again thank you, Melchior, for this presentation. Also, thank our first speaker as well again. So thank you both for this these very nice presentations on our last IMFSE seminar for the year. And I'll just try to share my screen for a second as a very short recap of the last year. So if all is well, you're seeing this screen now. This was where we set out a couple of months ago already. The Fire Safety Day this year being online, still having this link between the IMFSE contributors, the students, the sharing of ideas, getting to know the companies. And we have had a large number of very different presentations, different sides of fire safety engineering, from testing of structures to radiation calculations to actually talking about the beauty really of CFD. These were some of the first ones. Here we continue, some more presentations also this year, amongst others by ATEX, by Gay Engineering, by University of Edinburgh. And it brings us to today, really. So today we had the two last presentations, and I would like to thank the presenters of today again for that. And I would also specifically like to thank Balša Jovanović and Liz de Kroos, who have, as always, provided lots of support for the different seminars, preparing the posters, following up with the invitations and so on. So again, thank you, Balša, thank you, Liz, thank you to the IMFSE contributors, and thank you all for joining us throughout the year. We'll get back to you in the near future, in a sense that hopefully then we will in the end have in-person events in the coming year. But for now, again, thank you all to join us this year in the online seminar series, and talk soon. Thank you. And with this, I'll then close today's session. Thank you all.